We spent some time last week talking about what I call multi-force problems, problems where we have more than one force acting on an object. When we have that kind of a problem where there's more than one force acting, we always need to draw what we call a free body diagram. Free body diagram is what? What does it show? Shows all of the forces acting on the object. Now, sometimes we also include other information like the mass of an object or the acceleration, but the free body diagram technically only needs to show the forces. The reason that I draw or that I include the mass sometimes, the acceleration, whatever it is that we have, is because, look, I got to write down my givens somehow. I might as well, if I've already drawn a diagram, I might as well just include it with the diagram. Let's say we got a box. And this box has a mass of 10 kilograms, which remember isn't actually necessary for the free body diagram, but I usually put it in there anyways. That box is being pulled on to the right by somebody with a force of 100 newtons. We're going to say FA is to the right with a force of 100 newtons. Maybe we could have called that F1. Maybe you could have called that FP or FQ, or whatever you want to call it, right? It doesn't matter. Okay, I call that FA. Let's say somebody else is pulling on that box with a force of 50 newtons to the left. Well, we got to draw another arrow to the left. What do we got to make sure that we do? Shorter, right? Shorter to indicate that it's going to be a smaller force than FA. There's friction acting on this box. A force of friction of 20 newtons acting on this box. Which way does the friction act? Against what? Against FA. Why does it act against FA? Why does it act against FB? Yeah, it helps FB, right? It acts against the motion. And if we have a force to the right that's bigger than a force to the left, it's going to move to the right. Friction is therefore going to act to the left. So we're going to say that force of friction of 20 newtons is to the left, opposite to the way this thing is going to move. Are there any more forces that we have here? We have gravity and the normal force. What do we know about gravity and the normal force, however? Yeah, they're going to cancel each other out. We'll say Fg is downwards, Fn is upwards. We can draw the normal force gravity somewhere else if we want, but in the end, they're going to be the same length, and they're going to be the same magnitude, opposite direction, which means they're going to cancel each other out. When we can cancel something out of our free body diagram, you should do that to simplify it. Gravity and the normal force every time so far have canceled. That won't be the case always, okay, but it is right now for us at least. And again, we'll deal with it. We've talked about this a number of times. We'll deal with it when we come across a situation where they don't cancel out. All right, what's next? Now that I've drawn my free body diagram, showing all my forces, canceled out what I can cancel, what balances. What's next? Son? Yeah. And how do I find the net force? Yeah, just like when we were finding my net pay or your net pay, we add up everything. The net force is the sum of the forces. FA plus FB plus FF. I made those alphabetical. Does it matter? Could I have made it FB plus FF plus FA? Sure. What's 1 plus 2? 3. What's 2 plus 1? 3. It doesn't matter what order we add them in, right? Now, if I'm looking for the net force, I'm just going to plug in my numbers at this point and solve. But if I'm looking for the acceleration, what's the next step that I'm going to follow? Yep. Yeah, we know that F net is equal to the sum of the forces, but it's also the same thing as M times A. So we'd replace F net with MA this time. FA plus FB plus FF. Now, I don't want to solve this question entirely here, but of course, I'd plug in my value of mass here, 10 kilograms. What would FA be? 100 newtons. What would FB be? Negative 50 newtons because it's to the left. And what would FF be? Negative 20 newtons. And then plug in all those numbers. Make sure you include the signs and then solve for the acceleration. All right? That's almost exactly like the question that you had for homework over the weekend, except that that question that you had for homework over the weekend had some extraneous information, some information that didn't actually matter. It was meant to try to trip you up, these mean people that wrote this book. It's good, actually. I like the fact that they do that. Because we see that from time to time, especially as Physics 20 and especially as Physics 30 goes on. We see stuff in questions that doesn't really matter, and we have to figure out what matters and what doesn't here. All right, so let's read through this. It says, in a men's four-man bobsled event in the Winter Olympics, the maximum mass of a bobsled with 2 riders, a pilot, and a brakeman, so 4 people total, is 630 kilograms. During a practice run, riders A and B exert average force of 1220 and 1200 newtons forward. To accelerate a bobsled of this mass, a pilot and a brakeman, 97 kilograms. Then they jump in for the challenging ride down the 1,300-meter course. During the pushing, the magnitude of the force of friction acting on the bobsled is 430. We want to find the acceleration of the bobsled, the pilot, and the brakeman. So picture what's going on here. Here's the bobsled. It's a rather boxy bobsled, not very aerodynamically sound, but these guys are, man, they're pushing it so hard it doesn't even really matter. And that's how good these guys are. We got one guy, we're going to call it person A, pushing forward with 1220. We got another one pushing forward with 1200, so we're going to make that one just a little bit shorter. Call that FB. Again, you can call it whatever you want. They use riders A and B, so we might as well use the same notation probably. Any more forces acting here? Yeah, there's a couple things actually. 2 or 3 more things. What else is acting here? What else is acting there? Yeah, normal force and force of gravity. So gravity acts down, and the normal force is acting up. And we know they cancel each other out, right? So I'm going to cross those off. Anything else? Right, what else we got there? Besides FA, FB, FG, FN. Yeah, the value of friction is 430. Which way is it going to act? Yeah, so let's draw that, I don't know, smaller than the 1200, obviously. Let's call that FF. Now, I don't have to include the mass on my diagram. I can include the mass somewhere separate, but I might as well. What is the mass that I use here? Is it 630? Is it 255? Is it 98? Is it 97? Is it some kind of combination of those? What mass am I going to use here? Okay. And the mass of the brakeman? Yeah, so we're going to use a total mass of 450 kilograms. The mass of the bobsled, the pilot, and the brakeman. Why do I not use the 630 kilograms here? Jack, why do I not use that?
Because that's not the actual mass that they are. It's just saying that that's the rule maximum they can have.
Yeah, that's a rule. That doesn't mean that that's the mass. Listen, don't ever use a mass unless they tell you this is the mass. Just because it could be the mass, it doesn't mean it is the mass. Okay, the color of this bobsled could also be red. Does it matter? No. So the mass that it could be doesn't matter either. Does that make sense? What matters is the mass that it is, not the mass that it could be. So we're going to include the 450 kilograms. What about this 1,300-meter course? Does that matter? No, there's a couple things in here that don't matter, right? Kind of like the color of the bobsled, red or blue or yellow. What's next? Laura, what's our next step there? Yeah, the net force, the total force, whatever you want to call it. It's the same thing. FF plus FA plus FB. Should I put these ones in alphabetical order? No, it doesn't matter. You can if you want. It doesn't matter. 1 plus 2 is 3. 2 plus 1 is 3. Now, Since I want to find the acceleration, I'll say m times a here as well. If I was just looking for f net, then I'd leave it the way that it was. Some of you, as you're writing this, are probably just going to skip that first line there. Okay, I'm going to always write that down because I think that it helps us to understand what net force really is. If you skip that first line, I can live with that. If you skip both of those lines, then you're going to lose a point. M is 450. The acceleration is, that's what we're looking for. FF is 430. FA is 1220. FB is 1200. Is that right? What's wrong? Yeah, 430 is a negative value because it's going to the left, right? Okay, that's one of the benefits of having that free body diagram is that, first of all, we see, like in a quick little summary, what the forces should be, but we also see what direction they are. We've already thought that through, and because we have, we realize that it is a negative value. Solve for A here. All we're going to do is add up what we have on the right side and then divide by 450. And when we do that, we end up getting 4.4 meters per second squared to the right. Good. How many people got that? Good. Yep. Yeah, on a slope, the normal force and gravity would not cancel. You're absolutely right. Does it even say? Yeah, it doesn't really say there. So you'd have no way of calculating the normal force. You wouldn't know how, even if you did know what the slope was, you wouldn't know how to find the normal force right now, but you will actually soon. You'll be able to do that. But since we don't have any information about that, we're just going to assume that it's horizontal the whole way, which is of course not true. But take a look right now at questions 1 to 4 and 8 on page 136 for the next 10 minutes or so, all except for question 2B. So 1, 2A, 3, 4, and question number 8.